Alright guys, so today we are going to go through the solutions notes. Your warm-up was, in your own words, to use what you know to write a few sentences about what a solution is. And so typically students tend to write things like solutions are answers to problems and that sort of thing. And some people hit on the right path and talk about mixtures and that sort of thing. In today's notes, we're going to hear a lot about exactly what solutions are. Make sure that you're filling in the blanks on worksheet or booklet 8 as we go along through these notes. Today we're going to cover the notes and we'll stop right before the calculations. We'll do the calculations next week. First we pick up with solutions, right? A solution is a homogeneous mixture. We have two parts of a solution. We have a solute that is dissolved in a solvent. Okay, and so the solute is the substance being dissolved, whereas the solvent is the liquid in which the solute is being dissolved. Okay, an aqueous solution has water as its solvent. Okay, and so if we think about making a glass of Kool-Aid, right, which is definitely a solution, the substance being dissolved would be the Kool-Aid powder. This would be your solute. The substance that it's being dissolved in would be water, so that would be the solvent, and it would be an aqueous solution because our solvent is water. Next, we talk about solvation. Okay, this is the process of a solvent particle surrounding the solute particles to form a solution. Okay, or the process of a solution being formed. If you look at the picture all the way to the left, we see that we have molecules that are real close together. That's our solid being introduced into our liquid. Okay, and so the process of solvation is basically just the process of it dissolving. As we progress to the second picture, we see the molecules start to break apart. The third picture, the molecules are way spread out because it's completely dissolved. So solvation is just another way of saying dissolving. Next, we look at solubility and how things generally dissolve. And what we like to say in chemistry, a general rule is that like dissolves like. Like refers to the solvent, right? And the solute being either polar or nonpolar. So a polar solvent will dissolve a polar solute. A nonpolar solvent will dissolve a nonpolar solute. Like is going to dissolve in like. Water is going to be a polar molecule. And so water is going to dissolve things that are polar because like dissolves like. Water is also considered the universal solvent because water is really good at dissolving things. Most things, if they're dissolved, can dissolve in water. Now this slide kind of talks about if something's going to dissolve or if it's not going to dissolve. When substances combine, they can either be soluble or insoluble. We've already covered this in a previous unit, but just to kind of review this, soluble is when a substance will dissolve in a solvent, okay? When that solute actually dissolves in the solvent. Insoluble is when it doesn't dissolve in the solvent, okay? The solute will not dissolve in the solvent. Like I said, this is review. You should remember this from a previous unit. Next, we talk about the rate of solvation. The easiest way to describe this is it's basically the rate at which something dissolves. Some factors that affect solvation are dissolving, agitation, right? So stirring, shaking, allowing particles to dissolve faster, right? That definitely helps. We can increase the temperature. Heat's going to add energy, which allows particles to move faster. Except for gases, right? Gases are a little different. They're going to dissolve better at colder temperatures. And then number 3 is particle size. The smaller the particle, the more surface area, and so the quicker it's going to dissolve. And so all of these things are different items that can affect the rate of solvation or the rate at which something dissolves. We can stir it, it makes it dissolve faster. We can increase the temperature, and we can crush it so that the particles are smaller. All of these things will make things dissolve faster. Next, we can take a look at a graph of temperature and solubility. As you look at this graph, you can tell that as we increase the temperature, which is the variable on the bottom, our solubility is going to increase for potassium nitrate and lead nitrate. Now, sodium chloride doesn't affect it as much, but in general, looking at this graph, you can say that as we increase temperature, solubility is going to increase. Solubility, here's a formal definition for it, right? It's the maximum amount of solute that will dissolve in any given amount of solvent. We usually look at 100 grams whenever we're talking about solubility, okay? So it's the max amount of solute that can dissolve in a solvent. That's what we call solubility. Some terminology for solubility. We have 3 different terms we look at: saturated, unsaturated, and supersaturated. These 3 are important, and they almost always appear on the test. So a saturated solution is going to contain the maximum amount of dissolved solute, right? Meaning it has the most that we can possibly put in that solution. An unsaturated solution contains less than the max amount. Supersaturated contains more than the max amount. And the easiest way to think about this is to talk once again about that Kool-Aid, right? If we have Kool-Aid where we mix in just the right amount of sugar, just the right amount of Kool-Aid powder, okay, and we put as much as we possibly can without putting too much, then that would be considered a saturated solution. It's going to have the maximum amount of the sugar and the Kool-Aid powder. Now, an unsaturated solution would be like bad Kool-Aid, right? Kool-Aid that's probably not very good because it really just tastes like colored water, okay? We're going to have less than the max amount of the dissolved solute. Now, supersaturated could be some nasty Kool-Aid too, unless you like your Kool-Aid crunchy, right? Supersaturated is when we would have more sugar and Kool-Aid power than the water could possibly dissolve. That means it would be crunchy, right? Because not all of the solute would dissolve in that solvent. And so that's your difference. Saturated has the max amount possible, but not too much. Unsaturated is less. Supersaturated would be more. Now, here we're going to look at this graph and talk about what type of solution, right? We want to look at it and determine whether they are saturated, unsaturated, or supersaturated solutions, okay? You will be required to do this on your test, so you want to make sure you're paying attention, okay? For this one, it says, what type of a solution is a solution that contains 70 grams of lead nitrate at 40 degrees Celsius in 100 grams of H2O? We already know it's in 100 grams of H2O, and so we're going to plot our point here. So 40 degrees Celsius and 70 grams. You want to plot this point on your graphs in your notes as well, right? So 70 grams, 40 degrees Celsius. It's going to land. So our point is going to land right where our 40 and our 70 meet, and so right around there, okay, roughly speaking. All right, and so in this case, our point lands on the line. And so when our point lands on the line, that means our solution is going to be a saturated solution. All right, and so you might want to make a note in your notes that when it's on the line, it's a saturated solution. Very, very important that you remember that. So since our point lands on the line for lead nitrate, that means it's a saturated solution, meaning we have the maximum amount without having too much of solute in our solvent. So, like I said, it's saturated. Moving right along, this next one, sorry, the text came up on top twice. I'm not sure why that happened. But the question says, what type of solution is a solution that contains 20 grams of sodium chloride at 80 degrees Celsius, right? And so we're going to do the same thing here. We're going to plot our point. And so we're looking at 80 degrees Celsius and 20 grams. So our point is roughly there. And so our point is going to fall below the line in this case, right? Because we're looking at sodium chloride. And so since our point falls below the line, this is going to be what we call an unsaturated solution. Okay? And so anytime your point falls below the line, you might want to jot this down, it's going to be an unsaturated solution. Whenever your point falls below the line, it's going to be an unsaturated solution. Alright, so our answer there, once again, is unsaturated. Now this last one says, what type of solution is a solution that contains 120 grams of K2NO3 at 60 degrees Celsius, right? And so we're going to do the same thing. We're going to plot our point roughly. And so 60 degrees Celsius, 120 grams. Our point is going to be right around there. Okay. So in this case, our point is above the line. And so since this one is above the line, that means this is going to be what we call a super saturated solution. Okay, so if it's above the line, you might want to make a note of this once again. If it's above the line, it is a super saturated solution. So once again, super saturated. Moving right along, now we're going to spend a little bit of time talking about properties of water. Water is a very special molecule, and we're going to talk in detail a little about each one of these points. Its structure, the hydrogen bonding, cohesion and adhesion, surface tension, polar solvent, high heat capacity, and capillary action. The molecular structure of water is very unique. We have one oxygen atom, two hydrogen atoms. The formula is H2O, right? It's not going to be totally symmetrical. Electrons are going to spend more time near the oxygen and less near the hydrogen, right? Which is what makes that water molecule polar, okay? Your water molecule is going to have a slightly negative charge near that oxygen and a slightly positive charge near those hydrogens, right? Which makes it a polar compound. Because of that polarity and that positive and negative charge, water is very unique in the fact that it can undergo hydrogen bonding. Hydrogen bonding is what gives water all of the really cool, unique properties that it has. So what happens is the negative end and the positive end, right, have charges. And so the positive part from where the hydrogens are going to form this hydrogen bond with the negative portion of another water molecule where that oxygen is, and that's what we call a hydrogen bond. So each water molecule is going to bond using hydrogen bonding to its neighboring molecule. This makes water very, very unique. Water also has a property called cohesion. This is when water basically attracts to itself. And this is once again because of that those hydrogen bonds. And so cohesion, a wave is because of cohesion, right? Because the water molecules are attracted to itself. Next we look at adhesion. And this is when water molecules are attracted to other substances or other surfaces. You can see in this picture the toothpick, when it's stuck into the water molecules actually adhere to the backside of the toothpick, and so that's what we would call adhesion, because the water is being attracted to the surface of the toothpick, and that's what we call adhesion. Next we look at surface tension. Surface tension is very interesting. This is when we have an interaction between those hydrogen bonds and the Earth's gravity. And so what surface tension does is it allows spiders to walk on water. It allows a paperclip to float on the top of the water. And until that surface tension is broken, stuff like that can happen because the water molecules are stuck together with that hydrogen bonding, and then the Earth's gravity kind of forms that surface tension. Next we look at solvent properties for water. Water is a polar solvent, meaning that it dissolves polar solutes. Nonpolar solvents dissolve nonpolar solutes, right? We said that before, so like dissolves like. And so water is going to dissolve any solute that is polar. Next we talk about the heat capacity of water. And it has a very high heat capacity, right? A very high specific heat. Remember, specific heat is the amount of energy required to change the temp of 1 gram of a substance by 1 degree Celsius. This is kind of kicking back to thermochemistry a while back. And the reason we're mentioning it now is because water can absorb a lot of heat before it starts to get hot. And that's because of the way water molecules are bonded together. Next we look at capillary action. This is the wettable surface that causes a film of water to partially pull away from other water molecules and cling to the surface, right? And so this is how plants drink up their water. Capillary action is important in our soil and our plant-water relations. Another thing that this might look like, and it looks like it because it is whenever you have a graduated cylinder. This is the reason that the water is going to cling to the walls of that graduated cylinder, and this is what causes the meniscus in a graduated cylinder. So the capillary action causes the edges of that container to kind of attract the water, causing that dip down in the middle. This is what we call capillary action. Alright guys, we're going to go ahead and stop here. This warm-up will be for later on. That's going to be it for our solutions notes. We still have some calculations to cover. We'll cover them Monday and Tuesday of next week. For the rest of the period today, you need to go ahead and work on worksheet 9. The biggest part that you want to remember is that a saturated solution falls on the line, a supersaturated solution is above the line, and an unsaturated solution falls below the line. The rest of the stuff on worksheet 9, you should be able to use your notes to help you go ahead and complete it. Worksheet 9 will be checked when I check your notebooks next week, so make sure you get it done and get it taped in your notebook. Y'all have a great weekend.